So the main topic of today is constraint satisfaction. And my goal for today was that I'm going to do this set on constraint satisfaction. Actually tell you about a really nice constraint programming language and a software that is implemented for that. And we'll also do some constraint optimization. If we don't get to constraint optimization, then we'll think about it. We'll do it another time or skip it. So constraint satisfaction. Now let's think about what we have accomplished so far. What we have accomplished so far is that we have created atomic agents. We did not go inside the state space. We said that we are going to assume that there is some black box that is spitting us the states and neighborhood functions or successor functions. And maybe some more information about the domain, like the heuristic function. And then we are going to exploit that to solve the problem. Just that. This is definitely a starting point. It's atomic. We are not making any assumptions about the domain. And we created algorithms where we can, with this minimal information, actually solve pretty much every problem, at least every deterministic problem. So a thesis that often people have, at least the traditional minded people in AI, is that AI is nothing but search. And that is where it comes from. Because the basis of a lot of what people in AI do is search. Now, we also made this connection, or we at least discussed it in the first class, that just by using this formalism, we may not end up solving the problem. And the reason we may not end up solving the problem is because, yes, it is search, anything is search, we can solve it using search, but the state space is so large that we will never be able to solve using just basic search. So, what do we do? The solution, or one way of thinking about it, is that there is a lot of structure in the problems. And by just defining the atomic agent that is only using the black box as for state and successors, it is not using that structure. So what does structure mean? What kind of structure are we talking about? So what people in AI do, or at least a lot of traditional research in AI was like this. They will define a subclass of problems, which is still general. We're not talking about the specific problem of creating a robot which can answer questions related to, soccer. No, I'm not talking about that level of detail. Some general formalism still, but still a specific formalism which is less general than this high-level atomic agent that we have discussed so far. A formalism in using which a lot of problems can get expressed, but not all, or potentially not all. And then what we will do is that we will use this representation to have more knowledge about anything that gets expressed in this representation. Go into the algorithm. Now, I'm giving you a very abstract view, but we make it concrete in a minute. And so a lot of the people say that AI is search. Equally many, a lot of the people say that AI is representation. This will be very confusing initially, but we'll keep working on it in due course. We as humans are intelligent because we are able to see what are the characteristics of the problem and create heuristics and ideas, intuitions based on this particular problem. If we want the agent to get the similar capability, what we need to do is to define a representation in which many or any problem can get expressed and have the agent exploit the specificity of the representation in its algorithms. And that is also equivalent to saying I'm going inside the state, I'm creating more structure within the state. So we are no longer an atomic agent. We are going to be an agent solving a specific kind of problem that is represented within this representation. And one manifestation of this general abstract mumbo jumbo that I'm giving you is constraint satisfaction. So let's discuss constraint satisfaction, and then post-process it and see whether what I just said made sense in the light of CSPs. And in and of itself, CSPs are interesting. And CSPs are interesting because if we can solve CSPs, then we demonstrate intelligence. And we'll talk. So this is the outline for this set of the slides. I'm going to tell you what CSP is, what is a constraint satisfaction problem, and then I'm going to spend a lot of the time discussing. I'm going to define it as search. Everything will be defined as search for the next couple of weeks, and then we are going to use the problem structure, the representation, and other structure in my CSP to make the algorithms more tractable or to make them faster. And then we'll just do a little bit of local search. Okay, so this is the roadmap. What's a constraint satisfaction problem? So as we just said, in an atomic agent, a state was a black box. It could be anything. Now a state is not a black box. We are going inside the state, and we are saying that a state has n variables, x1 to xn. And each variable can have values from the domain dn. I also have a set of constraints in my problem, and my goal is to assign each xi with some value so that all the constraints are satisfied. That is my goal test. So now I have gone inside the goal test also, I have gone inside the state also. And so this is a very simple example of a formal representation language. As I was saying, AI is representation. Right? So the representation here is that my state has xi and its values dn. That's a specific kind of representation that I'm talking about. And because now we have a little more to play with than just state, which is a black box, we can exploit the fact that we have this information to create still general purpose algorithms that will work for all the problems that can be expressed within this state representation, but they will have more knowledge and therefore they will be faster than the basic standards are. That's the goal. This will be a running example. It's a map coloring problem. Are any of you from Australia? Has anybody lived in Australia? Okay. So you have an added advantage today in the class. Okay. Because you will remember the names of all the states much better than all of us. So for the next 1 minute, please try to memorize these names because we'll talk about it over and over and over. We have Western Australia, the Northern Territory, the Southern Australia. These are easier to remember. Then we have Queensland, New South Wales, Victoria, and Tasmania. And so these are our variables. Western Australia, Northern Territory, Queensland, New South Wales, Victoria, South Australia, and Tasmania. And we want to do 3 coloring. So we are allowing red, green, and blue to show up in any of these states. And the constraint is that no adjacent states can be colored with the same color. So standard map coloring constraint. So we can represent it by saying that WA should not be equal to NT. Or we could say that WA and T can take values between red, blue, green, red, green, blue, green, green, sorry, not green, green, whatever, but it cannot take values red, blue, blue, or green. So there are multiple ways of specifying the same thing. The idea is they cannot be colored the same. So this is a CSP. We have 7 variables, 3 values for each variable, and some constraints. And we want to find a solution where we have the assignment to all these variables such that all the constraints are satisfied. So everybody see this as a CSP? This is a solution. Associated with each CSP is a constraint graph. This constraint graph tells us how are the constraints affecting the variables, how are the variables placed with respect to each other. So here I am showing a constraint graph for a binary CSP. And the reason I'm showing you, okay, let's stick to that. And so binary CSP means that each constraint only relates to variables. So here WA not equal to NT is a binary constraint because it's only relating to variables. And so this tells me that there is a constraint between W and NT, there is a constraint between NT and Q, there is a constraint between Q and NSW, but there is no direct constraint between Western Australia and Victoria because they are not adjacent to each other. Yes.
So constraint graph is only for binary CSP, right?
No, I have just defined a constraint graph for binary CSP so far.
Can it be for more than binary?
We can create a new graph which shows you the constraints. We'll just show how to represent it. But you're running ahead of me, but what I would tell you or show you is that any CSP can be converted into binary CSP, and so just dealing with binary CSP is good enough for us.
And so arc means edge, right?
Yes. Thank you. Now CSPs come in a variety of forms. One is a discrete CSP with finite domains. So discrete CSP with finite domains is what we have defined. Satisfiability is another example of that. Every variable can only take true or false. We'll talk about satisfiability the whole class next time. We can have CSPs with discrete variables but infinite domains, like integers. So job scheduling, you have start time, end time, and let's suppose they're all integers, then you will have constraints of the form that you cannot start job 3, so you have to start job 3 within 5 units of time of job 1 and so on and so forth. You can have continuous variables where you have real value, like starting and end times of Hubble telescope, and so on and so on. So basically CSP is a general formalism. It can allow for discrete, infinite domains, all kinds of domains. We'll stick to discrete, but people have thought about continuous. People in the AI community also have thought of continuous. We will not get into that too much. Then there are different kinds of constraints. So South Australia cannot be green is a unary constraint. It is saying that this particular variable cannot have this value. Binary constraints like South Australia cannot be the same as Western Australia. Higher order constraints like all of these, like 3 cannot be together, or various kinds. There are many higher order constraints. One of the very interesting higher order constraints is called the all-diff constraint. It says that these variables should all have different values. It's a very famous, very important higher order constraint. Another higher order constraint is at most k, like this thing cannot be assigned to more than, this machine cannot be assigned to more than 4 jobs, and things like that. Then there are soft constraints, which says, you can color it anyway, but I really like red. It's my aesthetic choice. So if I can put more red in there, I'll be happier. That's a soft constraint. And that leads to, so that is often represented by cost of a variable assignment, and that leads to constraint optimization problem as opposed to constraint satisfaction. And if we spend 3 hours on constraints today, I would have definitely discussed constraint optimization. We'll see whether we can get to it next week. Here is another example. Okay. Have you seen these cryptarithmetic problems? Right? One of the ones that when Cold War was still happening when I was a child, there was a very nice cryptarithmetic problem which said USA plus USSR is equal to peace. So that is quite nice. But anyway, this is an example. 2 plus 2 is 4. We all know that, of course. But the goal is to assign a different numeral, a different digit, to all of the symbols so that this sum is accurate. So what are the variables? T, W, O, F, U, R. 6 variables. And actually more than 6 variables. Interesting. Okay, so in order to make this work, the domains are all 0 to 9, and there's an all-diff constraint which says that T, W, O, F, U, R have all have to be assigned different values. But then you have to talk about the constraint which is that the sum of this and this letter is this letter and so on and so forth. So how do you do that? So one way to do this would be to say 100 times t plus 10 times w plus o is equal to 1000 times f plus and so on and so forth. Right? Basically saying that this is a correct addition. So if my constraint language allows such a constraint which is represented with addition and so on and so forth, that's great. But suppose it doesn't allow, then what could I do? Well, I can define variables x1, x2, x3 which are the carry for each of these points. So then I can say that O plus O should be equal to R plus the carry x1 times 10. But now x1 can only, well, I guess x1 can be anything that you want. And so on and so forth. So that is another way to say exactly the same thing. If we do that, then we have to assign 3 new variables. And this is the constraint graph for non-binary constraints. So what we do, we define a join node here, which says this is a constraint that connects O, T, x3 and x2. So it's just a shorthand for that kind of stuff.
Can you explain the graph again? Like what does the rectangles mean?
Rectangle just means that there's a constraint which is connecting all of these nodes. So it's a way to represent non-binary constraints. Higher order constraints.
These are called factor graphs.
These are factor graphs. This is a factor.
So the binary one is a tree?
No, it's not a tree. And again, these kind of graphs also show up in probabilistic reasoning. And this is the interesting thing that we will sort of talk about more and more, that CSP and probabilistic inference have really close analogs with each other. In many ways, CSP is the deterministic version of the problem, and probabilistic reasoning is the probabilistic version of the problem. Any insight or many insights that you can think about in CSPs have an analog for probabilistic reasoning, and we'll talk about that towards the later part of the class. Now, the important point is that CSPs happen everywhere, all the time. They're extremely, extremely valuable. Every now and then, whether you realize it or not, you are solving a CSP. If you have to figure out there are so many professors, so many courses, who teaches what? You have to assign a course to each professor, the variables are professors, the values are the courses. It's a CSP, you have constraints obviously. Timetabling, this is very important. You have so many classes running in this university, which class is offered when and where. It's a huge CSP. In fact, it's less of a CSP, it's more of a COP, which is more of an optimization problem, because if somebody gave me a class that I have to teach at 9 o'clock in the morning, I don't know how many classes I'll be able to teach, because I usually wake up at 9 o'clock in the morning. So, and I'm sure there are people exactly opposite to me who sleep at 9 o'clock in the night. So, give me a second. So, it's often that different faculty members will have soft constraints. That, okay, if I have to teach it at 9, I will probably cry and teach, but I'll prefer to teach it at 6:30 in the night. So, what does that mean? We will have values for unsatisfying a constraint. So we can allow a constraint to be dissatisfied, but we will have to pay some penalty. That becomes a constraint optimization problem. So a lot of problems in the world, hardware configuration, you have to, you have the constraints of the space, but you want to put in these things together. Transportation scheduling, floor planning, job shop scheduling, machine and job scheduling. Basically, lots of scheduling problems. A lot of these things are CSPs. And more and more, the other thing is that CSPs are NP hard or harder, which means that any NP complete problem can be converted into a CSP. So even if it didn't look like a CSP, we can be smart and convert it into a CSP and solve it using CSP. So it's a very expressive language. We are going to solve very hard problems, and we still have more stuff. You had a question.
So is you not using some sort of software?
Everybody has to be using some kind of software. Airline scheduling, this happens in real routing. of which airline lands and takes off from which runway and what time. All of this is run by complicated software. Now those are somewhat of a dynamic problems also. So a flight may get delayed, and that is why it's not just basic CSP. You have to build on top of it. I don't know how UW uses it, but I'm sure it is using some software. I don't think somebody sits at a table and says, okay, these are the 10,000 courses or 5,000 courses we are teaching, let me by hand schedule them. I don't think
Well, they don't have to worry about cross-departmental usually.
There are some departments who do exactly that.
Yeah.
There's one person who's been doing it for years.
No, I'm talking about the large scale scheduling of classrooms and that might be. I'm not talking about assigning a course to a faculty member. I think that gets done manually because that gets done within a department, so there are only 20-30 people that we have to assign. Okay, so now let's start to have fun. How will you solve it? So we have defined the representation. We know what the problem is that we are trying to solve. We know that's a general problem. We can represent a lot of problems using this general formalism. How do we solve it? What is the first answer if somebody asks you how to solve a problem?
Search.
Which search? That is not the first answer. Your first answer is right. But now for this particular problem, how are we going to solve it? Think about it. Let's start with optimal solutions. Let's not do local search yet. I know you have been thinking a lot about local search, but let's start with the class before local search. So let's do systematic search. Can be formulated using systematic search. Samir.
Well, you have finite number of variables, so you can define the state as all of the domains, and each operator will be a simple change on one of the variables. Try.
Right. So that would be more closer to local search, although you can do systematic search over that too. Typically in these problems, we do incremental search, which means that we start with a partial assignment and then we assign the next variable. So instead of starting with a full representation, full solution, we'll start with a subset of variables assigned, or maybe no variable assigned. Then we're going to add one variable at a time and assign it. Okay? So let's pick some variable, assign a value, do search over that. Then make sure every constraint is satisfied. Then take another variable, assign some value to it, make sure every constraint is satisfied. If any point a constraint is unsatisfied, what do? We go back to the previous decision that we made, right? And repeat. You can call it depth first search. You can call it incremental search. It's the same. By the way, is it okay to do depth first search? What is the problem with depth first search? What is the maximum depth of this problem?
Number of variables.
Exactly. So we are now in a framework which has finite depth. All solutions are at which depth? N. All solutions are at N. So we can do, it's a nice ground, we can do whatever we want. So we can do depth first search because we may not be able to get that much memory to do breadth first search. There is no value to do breadth first search also because we know that all solutions are right. So let's start. Initial state, no assignment. Successor function, pick a variable, assign a value that does not conflict with the current assignment. And if no legal assignments exist, then no solution exists, go back up. This is the same for all CSPs. As we discussed, every solution appears at depth n with n variables. As you were saying, path is not important, so we could do the other formulation of complete search, but let's stick with that because there are very interesting things that we can add on top of it to make it work. At any depth d, the branching factor would be the number of remaining variables. Sorry, at any depth L, now d is confusing because D is also domain size. So at any depth L, the number of remaining variables will be n minus L. And let us suppose all of them can be assigned all values at that point. So the possible max value assignment is D. So my branching factor would be n minus L times D at depth L. Do you agree with this so far? I have assigned L variables, so the number of remaining variables are n minus L. I can pick any of them and assign them any value. So the number of successors will be n minus L times T.
Doesn't every variable have its own domain?
Yeah, but let's suppose they all have domain size T.
D is the maximum
Max domain size.
of any variables, at most you can have.
So why isn't the branching factor D?
You're just using.
Wait. So, if we did this assignment where we picked a variable randomly, we tried all variables and we tried all values to all variables, then the number of leaves will be n factorial d to the power n. Why? Because this d gets multiplied and this gets n minus 1, n minus 2, n minus 3 up to 1. So the total product will be n factorial d to the power n. First of all, that's large, that's huge. But second of all, it's wasteful. We are missing a critical insight in the way I have defined the incremental search here. What is the critical insight we are missing?
It doesn't matter which variable you assign which, the sequence in which you assign.
Yeah, order the variables.
You can order the variables. You don't have to try all variables at each point. And therefore, what happens is that your branching factor becomes just D as opposed to n minus L times D. And so number of leaves become D to the power n, which is how it should be, because that is the all possible assignments in your search tree. So anyway, if you didn't get the point of the slide, it's even better because you're not able to understand what mistake the slide was making, which is good. The high level point is that the right answer or a good starting point is what is called backtracking search. It's backtracking search is a name for CSPs where you are trying a pre-specified variable. So you know exactly which variable you're going to try next, but you're going to try different. You're going to search over the values. So here's the logic. Variable assignments are commutative. So if I did W equal to red first and then NT equal to green, that's same as doing NT equal to green first and then W equal to red. So let's pick the order. That gives us D to the power n leaves. And so depth first search with CSPs with single variable assignments is called backtracking search. It is the first basic uninformed algorithm for CSPs. And by the way, even this is not bad. It can solve n queens for n equal to about 25. Yes,
How do you convert the n queens into a CSP?
you tell me. What are the variables? Position of the queens in each column, let's say.
And the constraint will have to be represented.
The constraints will have to be represented. Not very hard to represent it. To make sure that no two queens are in the same horizontal, no two queens are, we have already ensured that no two queens are in the same vertical, so to ensure that no two queens are in the same angles. Alright,
Sorry, just a question.
yes.
What do you mean can solve n queens for n value equal to 25?
You can scale up to this point for whenever these slides were written.
Chessboard of 25.
Chessboard of
Right,
25.
so by a current modern computer.
By a computer 10 years old. Yeah, exactly. No, if you check Moore's law, we might be able to do 28 or 39 or 30. So, never mind. The point is, this is a good starting point. But we will talk about how to get to n queens up to 1000 at least. So let's see what do we need to do. So this is the basic backtracking search. I don't think we need to read this. This is easy. But the point is, if the assignment is complete, return it. Otherwise, select one of the unassigned variables which has been pre-specified by some logic. That logic we'll talk about what that could logic be. And then for each value, we will check if the value is consistent, add it, and recursive. There are many interesting questions, but before we do the questions, let's just make sure that we are on the same page. So this is our initial point, this is our initial state. Let's suppose we choose Western Australia first. So this is how our search tree looks like. We are doing depth first backtracking search. So let's say we go left, then we pick the next variable. We define, this is my search space now. Let's pick the next variable, maybe this one, or maybe this one. This is my search space, but we keep going left. And then if we don't find a solution, we come back and try other branches. So this is the depth first search. This is the search formalism to this problem. How can we improve the basic uninformed backtracking? We will not be putting in any knowledge from the exact domain, but we will be exploiting the knowledge that we have a certain representation of the state space. But what are the things that we can play with?
Adjust the amount you backtrack.
Sorry?
Adjust the amount you backtrack.
Adjust the amount you backtrack. What does it mean to play with amount you backtrack? Because if you didn't find a solution, you have to backtrack. You have no other option, right?
Right.
So what do you mean by amount you backtrack?
Backtrack, well, if you know which constraint is violated, you can go back to a state.
Right. So you're definitely running much ahead of us. There are people have thought about backtracking search and improvements to search itself by not doing just backtrack, by jump up much more up, like back jumping it's called, or conflict directed back jumping. We will not be talking about that. There is some discussion of that in the book, in the chapter, and so you guys are welcome to read. But let's just stick to backtracking search. What can we play with?
Which variable you choose next?
Exactly. That's the first thing to play with. Which variable do I choose? Do I select a random order ahead of time, or do I think intelligently about which next variable am I going to assign? What else? Very closely linked to which variable is? Which choice? Which value do I assign first? If I can pick the right values, then I just need to go down one path actually, not do any search, right? So by choosing the values intelligently, I might find a solution faster. Anything else that you can think of that you can play with? Yeah.
A bunch of the solutions are actually the same. They just differ by what we call the variables.
That's a great insight. What we will not discuss, what you will think about in your written assignment tonight is symmetries. A lot of CSPs have symmetries. It really doesn't matter whether I assign this dude red or green or blue, because red, green and blue are just symmetric at this point. So I can break the symmetries explicitly in CSPs, and we will not discuss it, but you will think about it tonight. But that's a great observation. One more that I'm looking for, yes?
If the graph is disjoint, whatever you call it, like Tasmania. Independent.
Very nice. Do you see that Tasmania has no connection with the rest of the graph? So I can just, whatever I want to do, I can do it completely independent. So if I have independence problems, then I can exploit that structure also in my search. That's actually a very nice thing. We'll get to that. But I'm looking for something else. Never mind. So these are the things that I want to do. And we discussed 1, 2, and 4, but we didn't discuss 3. Which variable should I assign next? Which value should I assign next? Can I detect failure early? And we will spend a lot of time on this. And then, what Mike just said, can we take advantage of the problem structure, like independence of problems? These are the 4 things that we are going to play with in the rest of the class. Okay? Everybody with me? Okay. So let's try and answer the first question. The question is, which variable should we assign next? Which variable do we hope Which variable is the most important to assign next? Yes.
The one with the most constraints attached to it.
Why is that good?
It'll cause the most failures in other branches.
If some variable is more constrained, it is trying to be picked up first. Because if we assign everything else and then come to this, most likely this variable will say, oh, you can't assign me anymore, I was the most constrained, then you should have assigned me first. How do we operationalize this? How do we know what variable is most constrained?
It takes part in most number of constraint situations.
It's a good thought. Hold on to that for one slide. Something else.
For example, diagram, you see like one of this linked to many other nodes, so that might be a very good candidate.
Yeah, you guys said exactly the same thing. You should speak more loudly. So, what you guys have been saying is that if something participates in more constraints, then that's a surrogate for most constraint. And you are right. I'm not denying it. But if we keep track of how many values we have for each variable that are remaining, then I have a more direct understanding of what is more constraint. What is that understanding?
Variable only has like one legitimate value left.
You have to assign it, right? You have no choice. So the less the number of values that a variable has remaining, the more constraint it is. And that leads to our first heuristic, which is minimum remaining values. So initially, every variable has 3 values. Let's suppose we assign Western Australia. Then, how many remaining values do we have for Northern Territory? How many remaining values do we have for, what was this, Southern Australia? How many values do we have for Queensland, yes. I thought Hui is going to help us, but that is not. Still 3, right? So clearly, if we followed this heuristic, we should assign one of these 2. Let's suppose we assign Northern Territory. Then this dude has only 1 remaining value. So we have to assign this guy. This is what the heuristic is telling me, that once you do this, don't jump onto some random node that is not related. Work with your graph, work with your constraints in order to choose the next node intelligently, next variable intelligently. So far so good? Yes?
Is this useful when you have countably infinite D?
Countably infinite D.
So it's still discrete.
No, so when you have countably infinite D, then what you do often is that you keep bounds. You keep lower bounds and upper bounds as opposed to individual values, because you cannot enumerate all values. And then if you wanted to use this notion of minimum remaining values, you will say minimum remaining interval. So the problems change slightly. That's why let's stick to discrete, because that's as much as we are going to get to cover in the intro class. Alright. Now I want to get to what you guys said. You can add on a second value, because what happens is the minimum remaining values is good, but often it will give you exactly the same numbers. Like for example, it gave you this and this. If I just asked you, I have assigned this guy red, what would you assign first, next?
South Australia.
Would you assign Northern Territory first, or South Australia, or you don't care? How many would assign Northern Territory first? How many don't care what we are going to assign? How many are going to assign South Australia first? Wow. You guys are intelligent. Or at least artificially intelligent. Why? Somebody.
More boundaries. That's why more constraints.
Exactly. You know that even though both of them has the same number of remaining values, one is much more constrained, and the reason it is much more constrained is because as soon as I assign these, all of these change. It's participating in a lot of constraints. So that leads to the secondary heuristic called the degree heuristic, which says choose the variable with the most constraints on the remaining variables. So now if we are starting from the beginning, minimum remaining values, all of them the same. So degree heuristic comes to play. In fact, it first assigns this guy, which is I think the logical step, ideally. And then we go on from there. Yes?
If you pick this strategy, do we need the one before?
Yeah, you first check minimum remaining values and then check degree heuristic. That's what has worked more or less.
Wouldn't it really say to them?
See, minimum remaining values is a much more direct measure of how constrained a variable is, but if there are two variables which have the same minimum remaining values, then you look for which variable is participating in more constraints. See?
Because you had three colors, it wouldn't matter if you picked the northern state in Australia, as long as you picked it within the next first three.
But that is very specific to this particular map and this particular thing. Notice, by this we build a strategy that will work for timetabling and that is going to work for, hardware. We're talking general stuff here. We're still getting intuitions from this particular problem, of course. Yes?
So if you say like Tasmania, we have a constraint that it can only take red or green instead of 3. Tasmania can have 2.
Right.
So will you start from Tasmania because it has?
Yeah, so that's in this the way we have defined it, yes. If we are not able to exploit the notion that they are independent subproblems, then they will start with this. Is that ideal? Probably not. That's why we want to use the notion of independent subproblems.
I think the book mentioned you always start from degree heuristic as the first thing. You don't even apply MRV to choose the route.
To choose just the route.
For just the route.
Okay, so I will double check. But the way I remember it, we start with MRV. If they are the same, then we do degree heuristic. Yes.
And don't we have to compute minimum remaining number of remaining values anyway to see if we're stuck? So we already have to pay the cost to compute this anyway. We might as well use it. If anybody has 0 remaining values, you're stuck. You have to backtrack. So
Yeah.
we're already computing.
We are computing. Of course, we are computing. So okay, let's get to the next part. So we have answered the first question, which variable to select. What is the next question? Which value to choose. Okay, Hiren, what would you suggest? So we selected the most constrained variable, but what kind of a value do we want to choose?
Was there still preferences?
No preferences, only satisfaction.
Least used.
Sorry?
Least used value?
Least used value, assuming you have inequality constraints, right? But your constraint may not be inequality. So what's the general mechanism? Yeah.
The least constrained value?
Least constrained value in some sense, right? So that's what the title of the next slide is. So dead on. So intuitively, we want the nicest value to start with, because the nicest value is most likely going to give us a solution. What does nice mean? Nice. So nice means that as soon as we add that value, it doesn't affect everybody too badly, the remaining variables. What does that mean? So to operationalize this, we will say that the one that rules out the fewest values in the remaining variables. So let's think about this. Let's suppose we started this with red, we got here green. Now we have the option of labeling this red, and why are we going in this order? Not important. Let's suppose we want to label this node next. We can label this node red, or we can label this node blue. Of course, we can't label it green. Which one is better?
Red.
Why is red better? Because as soon as we label this blue, this guy is not even feasible. But if we label this red, then this guy stays feasible. So by allowing this to be red, we are allowing no deduction from this node. By labeling this to be blue, we are allowing a deduction, and that deduction, so it's more constrained. The blue value is more constrained. So just by these heuristics, most constraint variable, minimum remaining values, degree heuristic, and least constraining value, we get to solving 1000 coins on a computer that was 10 years old. Yes.
So, to know what the future impact of a choice is, isn't that effectively exploring the tree anyway?
Yes. So
No.
So we will not be exploring the tree, but we will know the future impact, and we'll get to exactly how we do it. It's called, that's sort of the next step, called forward checking. So how do we keep track of what happens if we assign a variable? How does it affect the remaining variables? Let's talk about forward checking. So forward checking says the following. Keep track of remaining legal values for unassigned variables. Right? We were always doing that. But now we'll be propagating this information forward. And I guess we were doing that too. So, if we assigned Western Australia red, then we propagate this information and we know that now Northern Territory cannot be assigned red, Southern Australia cannot be assigned red. Now, by assigning Queensland green, we know that Northern Territory cannot be assigned green, New South Wales cannot be assigned green, and Southern Australia cannot be assigned green. Is this assignment feasible? Will this path gonna give us a solution?
No. NT and SA cannot use.
Exactly, right? But we don't know this yet. So notice that we have come down the search path, we have assigned some variables, but we haven't been able to detect failure, although we know that this is a failure, even in this small example. Let's keep going. We choose South
Victoria.
Victoria. Thank you. We choose Victoria and we assigned it blue. Then what happens? It affects South Australia. And we know that now South Australia cannot be assigned. At this point, we have detected failure. And we have detected failure early. So we have, so far our assignment is feasible. But we know that along this path, not much can be done. We will never find a solution. Why? Because Southern Australia has nothing in it. This is called forward check.
Tyson, so this seems like it wouldn't be very practical once you get into a high number of constraints, though, because you're just having to keep track of so many things, or a high number of nodes and constraints.
See, we are talking about a problem which has worst case complexity d to the power n. It is an exponential complexity. You tell me what is the complexity of forward checking?
It's the same.
Think about it.
What?
What is the complexity of forward checking? So I assigned it. So I assigned a new variable. I assigned a new variable a specific color, a specific value. What is the maximum number of remaining variables? N minus 1, n minus k, whatever. Order n. What is the maximum number of constraints in which this particular variable participates in? Say C, whatever, some number of constraints. How many values do we have for remaining variables? B each, n times d. So in the worst case, we will have to check what? C constraints and cut nd values. So in each operation we will be doing some order n, c, d kind of work, not too much more than that. And if that helps us detect failures early and we don't explore a d to the power n branch because of this work, I'll be very happy. So yes, it is costly. And notice that this is going to be the theme today. You can do full search without information and pay d to the power n. You can do some inference. And by the way, this is inference. This is saying that if I do this, then because of my constraints, I know that this will not be feasible. You can think of it as inference intuitively. So I can do a little bit of inference and reduce my exponential. Now I can do all inference ahead of time and not do any search, but then it will become exponential. So the idea is to do the right amount of inference so that I can detect failures early, I do not explore parts of my search tree and get savings. In the worst case, everything continues to be exponential. These are NP-hard problems. So this is a theme that is very interesting. That there is a search and there is an inference. We can do full inference, solve the problem, exponential. We can do full search, solve the problem, exponential. What is better is to have search and inference come together. So we do some inference within search, and that often works much, much better. Any other questions? Now, I come back to the same problem that I asked. So this is an infeasible. Assignment because we know that South Australia cannot have any remaining values, but forward checking is not able to figure out. Sorry, not just South Australia. NT and South Australia both have blue in there, and they both cannot have blue. So you and I can figure out that this is not feasible, but our machine is still not able to figure out because it is only doing forward checking. Now let's take the intuition. What is forward checking doing? Forward checking is propagating the constraints between a past variable and a future variable. What is past variable and future variable? Past variables are the variables that I have already assigned, and future variables are the variables that I have not yet assigned. Right? So forward checking is saying, I have assigned this red, let me say what it removes from others. So it's a constraint between this which I have already assigned and this which I have not assigned, and just removing its values. So it's a constraint between a past variable and a future variable, right? However, to infer that these two both cannot be simultaneously blue is a constraint between two future variables. So in forward checking, I have not used that insight yet. The question I am asking now is, can I propagate constraints between two future variables? We can, because we did it. Manually we did it. The machine should be able to do it. So how? That's called arc consistency that we are going to study next. But anybody has an intuition of what we might be able to do? Sean.
I was just going to say, this is sort of just the next step that you would take anyway, but as soon as you detect that you're down to only one case left, just apply that to your problem.
Yeah, but suppose I did not have inequality constraints. I had any other kinds of constraints. You have to come up with a general mechanism. I agree with you, but you have to come up with a general mechanism.
Just compare all sets of your variables and see, is there some combination that will satisfy each constraint?
Yes, yeah, pretty much there. Sets is too much. Let's do pairs first. So, the algorithm is called arc consistency. And the intuition is the following. So let's define an arc to be consistent, an arc between two variables x to y to be consistent if for every value of x there is some allowed value of y. If there is some value of x for which there is no allowed value of y, what can we do?
Remove that value on x.
If for some value of x we do not have any allowed value of y, then we can remove that value from x. Let's do the example, maybe it will become clearer. This is sort of the most interesting part of this lecture, so I want to make sure that you guys understand this. So let's come back to exactly this point. And let's do the constraint from South Australia to New South Wales, which means South Australia to New South Wales. Okay? So this is my x, this is my y. For every allowed value of South Australia, do I have an allowed value for New South Wales?
Yes.
So we can't say much at this point, right? Let's do the reverse constraint. Let's do the reverse constraint. For every allowed value of New South Wales, do I have an allowed value for South Australia?
No.
Which allowed value for New South Wales does not work? So what can we do? Remove blue. So just by this assignment and some propagation, some inference, I have realized that New South Wales cannot be blue with respect to what we have assigned so far. Let's keep doing. So let's do Victoria to New South Wales. Now blue doesn't exist. So for every assignment of Victoria, is there a value for New South Wales? Which value does not work?
Red.
So we get rid of the red. And we keep doing. So whenever we do this particular consistency, we realized that this blue cannot happen. And as soon as we realize this, we know that it's a failure. So, point number 1. Our consistency will detect failures earlier than forward checking, because it is testing for many more constraints than just forward checking. Of course, it will spend more time, right? And here's the other point. If x loses a value, so I was testing x to y, and I realized that there is some value of x for which there is no value for y, so I remove that value of x. Now, which arcs should I test next? Which are coming into x? Some w to x, essentially, all w to x. Why? Because now x has lost value, that means that whenever I test w to x, there will be some values for w for which there is no x anymore. Now, with this intuition in mind, tell me, what is the cost of inconsistency at each step? Let's assume only binary constraints.
D squared,
D square.
D is number of variables.
D is the number of values.
Oh,
N is the number of variables.
N squared.
N square. More than that. How is it N square?
Because each one you compare against, well, I guess it would be a bit more than N squared, because you compare each one against everything else, potentially more than one.
Okay, one at a time. So let's assume, suppose we know an arc that we want to compare. What is the cost of comparing exactly, testing one arc consistency? For each value of x, we have to go for all values of y. How many values of x do we have? How many values of y we may have? So the worst case cost of testing one arc is? So far so good. Each pair of variables will have to be tested potentially at least once. So we have at least n squared d squared. Right? Now comes the tricky part. As soon as we remove a value from x, we have to test its neighbors. Potentially n.
Wait, what is n?
N is number of variables.
But I thought you need to check only for the constraint equation, number of edges. Which is C.
So in the worst case, number of edges is n squared. So you can actually make this much more than it is. But as soon as I remove a variable from x, as soon as I remove a value from x, it's no longer d. So we are also reducing the domain size. So you can do the math, and what you will find is that it takes n squared d cube. And the reason it takes d cube is because
It's a function of how far you wanna go.
I just want to do arc consistency so that anything that I can propagate in each pairs of constraints we will have for each value of x we will have a value of y for all arcs. So okay, so let's make sure that I make the argument for n squared d cubed, right? So if I get rid of a value for x, I have to check the neighbors of x.
Once you modify it once, you might have to modify it again another time up to d, right? So you're running the entire algorithm, he says.
Right. So, but modify what up to d times?
So if you remove one variable and then you move further down your graph, and eventually one of the constraints propagates back to the same place where you started, then you'll have to do the whole thing again.
Right, exactly. So that is sort of the argument, and you have to do each arc at most d times. Because x to y, I remove one value of x, I remove more value of x, so basically each arc gets done about d times for each value of x, and therefore sort of the higher level argument becomes n squared d. So sort of the highest level, but I'm not making the
Could you run an arc consistency worker in the background? Just have it continue to remove arcs while you continue your other algorithm?
I don't think that's helpful because the point of arc consistency is to detect failures early, but if you're doing, search is much more costly. As soon as we add a search tree, then we have to do much more arc consistency. So by doing arc consistency in the background and moving forward, then
I mean, as you're doing search, you can just throw the nodes that you change into a queue and then pull those out and do arc consistency on all of them.
if we are doing search, it is much better to do arc consistency based on the assignments that we have already made, as opposed to. So the point is to reduce search. Search can take forever. So inference is reducing search. So I don't think it makes sense to do arc consistency slower. It makes sense to do arc consistency faster. Make sure that our thing is arc consistent before. Okay, so that's sort of the high level argument. Each arc gets removed at least once. And so d times an arc gets run, so it becomes approximately order n squared d cube, but you can be smart about it. So there are implementations which do much more bookkeeping, and that reduces the complexity to n squared d square. For there you have to sort of memorize for each x to y arc how many values of y and which values of y are consistent with each assignment of x. So as soon as they get reduced, you are not double checking everything. You check an arc only when you know that it's going to propagate and all of those things are gone and things like that. Yes?
So, looking at this algorithm, so we have the queue. So, d square is the amount of time it takes to check one pair.
Yes.
And the question is, how many pairs can we have?
N square
Uh,
at worst case. If you have.
So a variable is re-added at most d times, because d is the length of the domain.
Yes.
When you re-add a variable, the domain is shrunk by at least once.
That's right.
And so n into d is the number of times you can re-add something.
N into d
It's
is.
not really n, it's c, the number of constraint equations.
That is correct. That's correct. So we are sort of assuming that
So
we can
C-
have in the worst
yeah,
case
so
n
c
square
into d
constraints.
times is when you can, the number of variables that you can add, and take d square every time, so total is c d cube. So these are
C d cube is the same as n square d cube. So basically we are saying that in the worst case the number of binary constraints are n square, order n square. But you are right. If you are using C, then you can call it CD square, CD cube. Or it's also called ED cube. So E is the number of edges. So often when you read the CSP literature, they will say that the complexity of arc consistency is ED cube. And then it can be implemented faster using ED square numbers. So you are right, exactly
So
right.
you're using the fact that a completely connected graph will have n square edges.
N square, exactly. So you can have in the worst case n square. So I was just not getting too much into that, but you're right. You can call it ED. Yes.
You could have constraints that bring more than two variables together.
Okay, so now is a good time to make that detour. let me just show you that you can convert any non-binary CSP into a binary CSP. If this is my constraint, that the sum of A and B should be equal to C, I can define a new variable D, which is essentially pair of A and B. Okay? So now, this D will have a constraints with A, B, and C. What is the constraint of D with A? That its first number should be same as this guy. What is the constraint of D with B? That its second number should be same as this guy. What is the constraints of D with C? That its sum should be equal to C. So what I just showed you, proof by example, proof by whiteboard, is that I took a problem which had a ternary constraint. You can create new variables for pairs of these variables, and now I can convert it into a binary constraint. Now you can think of what happens if I had a fourth quaternary constraint, right? I will have one variable for AB, I may have another variable for ABC, and I may have constraints with AB, ABC, and so on. So that is why we are only talking about binary CSPs. That we allow, we are discussing this because you can convert anything into binary.
This you can do in linear term.
It would be exponential in the size of the largest.
Right.
Size of the largest what?
I mean, the maximum number of variables you have in a constraint.
It will be exponential in that.
I think so.
But you just put LHS equal to one variable and RHS equal to
Yeah, so I think that it's not how that works. If I have a constraint that connects AB with C, another constraint that converts AB with D, no, BC with D, no, I'll have to think about it. I don't want to, maybe you can think about it on the site and figure out exactly what will be that explosion. But most of us typically work with binary CSPs because we can usually. Alright, so we have solved. So we have answered the three questions that I started with. Which is the next variable to pick, which is the next value to pick, and what is the, how can we detect failures early. And in the process we also learned a little bit about search and inference. By the way, there's another point that you did not make, or maybe that is what you were trying to make and I misunderstood you. So what is arc consistency doing? Is arc consistency going to detect all failures early? So let us suppose I have two colors. And this is my graph, this is my map. So my colors are A, B, sorry, my nodes are A, B, C, and my constraints are A, B, C. Is this map two colorable? Can I color this map in two colors? No. Will arc consistency figure this out? Arc consistency.
Want to pick something for A?
Let's do. No, we not so just search. Just the inference part. Arc consistency. So it will test the arc bit from A and B. For A equal to red, do we have a value for B?
Yes.
For A equal to green, do we have a value for B? Is it going to remove anything? Similarly for AC, similarly for BC. So at the level of arc consistency, we will not detect this failure early. So there are still failures that we cannot detect with arc consistency. Why? Because each pairs are fine. But a certain set of three is not fine. So we can do what is called K consistency, which says, okay, I'm going to do all subsets of K and make sure that they have some satisfying assignment. So for all 1 to K minus 1 variables, I have some value for the last variable or whatever it is. Sorry. For each value for X, I have some assignment for remaining K minus 1 variables. Now you can see that that will start to be expensive, right? D to the power k, not d.
Complexity of 1 and
Exactly, precisely. Now you got it right. Search by itself was exponential. Inference, if you're doing inference over k, is exponential in k. You can do inference in n, that's still exponential. So that is the point that I was trying to make earlier. That you can take some complexity of search and put it in inference. You can take all complexity of search and put it in inference. What AI cares for is finding this balance point where you are doing some search and some inference and finding this middle point. And let me give you the highest level insight. What people have found is that it's okay to spend a quadratic amount of time in doing these inference problems. For some problems, it's okay to spend cubic amounts of time. But almost always it is not useful to spend more than that. In other words, if you are implementing a search algorithm, use our consistency, it will be immensely valuable. For some problems, use k consistency for k equal to 3, it may be valuable. But k greater than 3 will not be practical, by and large. So this is the highest level insight that people have found over time. It's okay to do binary constraints, our consistency about quadratic. It's sometimes okay to do subsets of 3, but don't worry about it. Why is that true? I don't know the answer, but we have seen that in a multiple set of problems. If we get to do planning, we'll talk about mutual exclusion. Again, it is checking binary constraints, but and this binary really helps for some. Alright, so now let's use some time and talk about problem structure. So one of the problem structures that people found, somebody, I forget who mentioned this, maybe you did, yes, Mike. What is that structure? Tasmania is an independent subproblem.
Connected components of the system.
Right. So a first insight that you can do is that look for your connected components in the constraint graph. So this is my constraint graph, and this is my constraint graph. Then what should we do? We should do 2 independent searches. No point in doing one search over all these set of variables because these constraints and these constraints are not talking to each other, they can be solved independently. And if you do that, that will be immensely valuable. For example, instead of doing d to the n of n, if you have 2 problems with n by n over 2 variables, what will be the time complexity? 2 times d to the power n over 2, which is really, really better. Now,
What's the complexity for finding the fact that you've got 2 independent
yeah,
graphs?
but obviously that will be NP hard. No, the connected component part will be very easy to figure out. So that's actually very easy. It's like order n cube or something. N square n cube. Again, DJ may remember. Tarzan's algorithm, is it?
Yeah, but I don't remember.
Yeah, some low order polynomials. It's pretty easy. Connected component business is easy. Unfortunately, in the real world, you rarely find these completely independent subproblems. If you have it, awesome. What will happen is that you will have something like this. Awesome. Now, if I showed you this problem, what might you do? So let's give them a name just for Tyler, right? Right. There is a Tyler. He's not here today. Yes, right.
I would start at G and then split it going up.
What does that mean?
Well,
Oh, you will start search at G.
I'd start search at G and then go in opposite directions separately.
So if we pick G as my first variable, what does that do? Once I pick G, let's say I assign it some value, propagate the constraints. As soon as I propagate the constraints, these constraints are no longer active. Now I have two independent subproblems. Figuring out the set to start with, which can convert it into two independent subproblems and is a good set, I'm sure that will help you.
You can probably do like a min cut or something.
Yeah,
You can think about fun things.
Min cut is maximum.
So, is it min cut? Right. So you can do min cut, and you can say that if I cut along this edge, then that has the minimum number of edges going. And then you assign all these variables, and then that sort of starts to. Good. You can do min cut. You learned something today. So that is one kind of structure that we can talk about. Here is another kind of structure. Actually, let's look at this. If I showed you this, what might you do? Assign which variable first? SA. As soon as you assign SA, what happens? You are left with a graph which looks like this. This is a tree, a path. This is a trivial problem that we are just going to see next. So that's the next step. It's called tree decomposition. Okay. So suppose each subproblem. We just discussed this. So we can split into two. That will be. What is this telling me? Suppose each subproblem has C variables out of the n. Okay, right. So then I have to do D over C, and I have to do it n over C times. So we had C equal to n over 2 in our example. So this is one example where if I had 80 variables, SAT problem, so everything is true or false. If I could divide it into 4 different problems, then 2 to the power 80 will take 4 billion years, 4 times 2 to the power 20 will take 0.4 seconds. So it can be immensely powerful, this identifying sub-problem business. But here is what we were getting to when we said we will choose SA first, and that was this notion of tree-structured CSPs. So here's the theorem. If the constraint graph has no loops, that is it's tree-structured, then this CSP can be solved in order n d squared time. Now we are close to exponential, we're talking low order polynomial, extremely low. So let's see how we can do this. The algorithm is rather straightforward. The algorithm is as follows. You hang the tree from some root node, like we did that for starting with A. So now we have A, B, then B goes to C, B goes to D, D goes to E, D goes to F. Basically assign some order, that is a topological order for this tree starting from any root. Now, you start from the last node and you do recursive arc consistency for its parents. So you say that I'm going to test the arc consistency D to F. For every value of B, I should have some value of F. If there's some value of D that does not work, I'm going to remove this. Then I'm going to test D to E. Then I'm going to test B to D. Then I'm going to test B to C. And then I'm going to test A to B. And I will keep removing the values from the parents. Okay? Once I have removed the parents, the values from the parents, then I'm going to start from this node and assign any value from the remaining set. Why is that okay? because I've already done arc consistency. So when I know that I'm assigning this value of A, I know that I have some value of B that I can assign now. That's what I check from arc consistency. So as soon as I assign this value of A, I remove the constraint values and I know there will exist some value of B that I can assign. I assign that value. Then again I know that for this value of B there is some value of C and some value of D. I can assign those and I keep doing this and I would have a solution for my CSP. How much arc consistency did I have to do? N arc consistencies in the worst case and N minus 1. Everything has at most one parent because it's a tree. And each arc consistency takes d square time, n d square arc consistencies, and then when we move forward, that I think even is faster. Order n d square. Pretty easy.
You want to find the cycles.
So now we know that we can solve trees very fast. So another way to use this problem structure is to say find a node that when assigned converts the rest of the problem into a tree. Now that may not be one node. So you may say that find me a smallest set of nodes that when assigned gets me the remaining tree to be a tree. And that set of nodes is called a cycle cut set. Yes?
What's the significance of doing topological search in the beginning? How does it help? As opposed to starting from a random node and doing parents?
Because I want to make sure that once I assign the variables, I will have values for the variables that come further, right?
So we start from the. So the end node is something which does not have any more child.
Exactly. So we can start with the full domain of D, but that will help me reduce some domain of full domain of F, but that will help me reduce some domain of D. If we start in the middle, then we may not have the problem. So okay, so this would be a cycle cut set for this. Then I can do search by choosing this first. Let's say I do red and green and blue, and as soon as I do that, I'm only going to pay nd square time for the rest of the graph. So if I knew this cycle and this cycle was say C nodes, then how much is the total cost of the algorithm? Well, I'm going to do search over my C nodes, so that will be D over C, and for each of those subproblems I'm left with a cycle, a tree, so that will be n minus C D square. However, finding the optimal cut set is NP hard. So life is pretty much more or less we get back to this NP hard business all the time, which is how life obviously will be, but these intuitions are very useful, and so whenever we can exploit any of the intuitions in making our CSP algorithm, then we will be able to be fast. And again, all of these intuitions go into Bayesian networks when we do Bayesian networks. There is a notion of cycle cut set, there is a notion of converting into independent subproblems, and so on. D to the power C is what values do I assign to the cut set. I have to do search over that, but for each assignment of variables to the cut set, I have a tree so I can assign everything else. Right? We have already discussed this. And that completes our discussion on constraint search. Using backtracking search, or iterative, not iterative, but sort of systematic search. Your question is?
So the book mentioned a theorem that if you are using forward searching, then you never require backtracking because all those things, all the cases of backtracking are foreseen by forward.
We just did examples where. Yeah, so there is a discussion on back jumping, conflict directed back jumping. You can read it. Usually what happens is that backtracking search with arc consistency is, I think, either equivalent or strictly stronger than conflict-directed backjumping. So in practice, knowing this set of algorithms that we have known is equivalent or better than that particular section. So I usually skip that section. We are welcome to read it. Right?
It can be proved that every branch proven by back jumping is also proven by forward checking.
As I was saying. So by knowing forward checking, we have sort of done the superset of back jumping and so on. So people took time coming up to exactly this set of methods which work out fast, and understanding the space. But what we have discussed is the right set of techniques for you to know if we are only doing half a lecture on this. But you are welcome to read this. This is interesting. There's back jumping, there's back marking, there's conflict directed back jumping. People have done a lot of algorithms in this space. But if you wanted to read further, I would say we can skip that section on back jumping and so on, but read about what happens when you are doing reasoning with time. What happens if you are doing reasoning with integer variables? That will be much more interesting and much more valuable. But it's not in the book. Now, the last thing that we need to discuss in this context is local search. And I don't think there's much to say. So tell me, how would we solve this set of problems with local search? You know this by now. You have a CSP, can you do local search to solve those problems? What will be a state?
We're talking about the Australia problem?
We're talking about CSP, any general CSP, discrete CSP. Can we solve it using local search? Alan?
You assign one value to each variable.
You assign some value to each variable. What will be the heuristic that I want to minimize or maximize?
Number of violations.
Number of constraint violations, number of conflicts, right? What will be an operator space?
Change the value
Of
of any variable.
any one variable, change the value of any one variable. What would be a good algorithm to solve it? Exactly, so you got it, right? Nothing terribly exciting. You know all this by now. Is it optimal? Is it always going to find a solution to eventually? Because of the, especially if you added some little bit of, because of the random restart. But if the solution is infeasible, if the CSP is infeasible, will we ever know it? Will we know it in the algorithms that we have done so far?
Yes, when the domain size shrinks to 0.
When we have done all our search and we couldn't find a solution, that is when we have guaranteed, we have proven that the problem is unsatisfied.
Actually, when the domain shrinks to 0.
But then we are doing backtracking, right? So
No, at that point in forward looking.
yeah, at any search node we know that we have detected failure early, but if we have detected failure, that doesn't mean that the problem is unsatisfiable. That just means that this branch is unsatisfiable. So we go back.
No, but if you keep doing R consistency and all, everything ends up being an empty.
As we just
When
demonstrated
you do
that
R
our consistency will
it
not detect
deletes-
all failures. Our consistency detects a set of failures.
No, but suppose we land up into that state where it ends up deleting everything. Then we know it's a failure, but that will not always be the case.
We can detect failures early in our search, but whenever we detect a failure, we know that this branch has no solution underneath it. But that doesn't mean that the problem is unsatisfiable. That means that the choices that we made leading up to this point are not the ideal set of choices. So we go back up and we come back down. And we keep exploring. At some point we go back to the root, we choose another value, and at some point we have exhausted all values for the root. That is the time we know that our problem is unsatisfied. Right? But local search will never know. So now if we did local search for n coins, we can scale up to 10 million coins. That is the point. So with all these things that we discussed for n coins, at least the first set of them, we could get to 1,000 coins. And I'm sure we can get to more with using our consistency and so on and so forth. But with local search, in constant time, almost constant time, we can get to 10 million coins. And that is the reason I want you to learn local search by heart. doesn't have the right properties. It is not optimal. It's not giving you a guaranteed unsatisfiable solution, but it's giving you something that is very, yes.
Yeah, but Queen is a particularly good problem for local search because the solutions are dense.
Okay, fine. So why don't you in your assignment compare local search with some version of a backtracking search in your assignment, and do it for really large number of bids and large number of companies and see what you find.
It's like I'm not convinced that the search problem we've got is dense. It's probably not. It probably is an optimal solution.
So what is the saying?
It is saying that I can find solutions to NQueens with a high probability, almost constant time, for very large n. But that's not saying.
What is the critical ratio?
Yeah, I've not gotten there.
Okay, sorry.
And that appears to be true. That appears to be true for any randomly generated CSPs. So now I am putting in a very interesting point here, and we will not delve on it this class. We will delve on it next class in much more detail. We'll spend about 1 hour talking about these random problems versus structured problems and what works better for what. So notice the what we have. It has, for now I'm just going to leave you with this experimental observation. That give me a randomly generated satisfiable CSP. Okay? And local search is going to find a solution for it very quickly for very large problems. Except if my problem is in this ratio, is in this, around this point. This point is called the critical ratio, and the surrogate for this is number of constraints divided by the number of variables. So as my number of constraints will increase, my problem will tend to become unsatisfiable, right? And as my number of constraints will reduce, my problem will tend to become extremely easy to satisfy. But as I increase my ratio where the problem becomes from extremely easy to extremely easy in the other direction. Around here, local search has a huge problem.
So is that when they're equal to 1? That when R is, when they're about the same?
No.
What is R?
R is different for different CSPs. For satisfiable CSPs, it's around 4 point something. And we'll talk about that a lot next class. Why does that happen? I don't know yet. It's called phase transition. This is the phase transition point, and we'll talk more about that. So this is an intuition that I want you to also capture. For random problems, unless you are in this really crazy place, local search is super awesome. But for structured problems, the same intuition may not hold, and moreover, you may be able to make incremental search, backtracking search, or those kind of systematic searches better. You may be able to make them work well for structured problems. If you thought about what kind of structure is there in the domain and propagated the constraints wisely. Okay, again we'll get back to that next class. So we'll end this discussion here. CSPs are a special kind of problem. States are defined by fixed set of variables, goal is defined by constraints. We discussed backtracking search, which is depth first search with one variable assigned per node. We discussed variable ordering and value selection. We discussed forward checking and arc consistency, which are ways to understand, guarantee later failure, detect early failure. This representation allows analysis of problem structure. For example, tree structured CSPs can be solved in linear time, ND square, and we can convert a problem into tree structured CSP by doing cycle cutset conditioning, and then local search problems are usually quite effective in practice. So this is sort of the high level executive summary of what we